Hello, everybody. We are here to discuss Chapter 11, the second part of Chapter 11, sections 11.3, 11.4, and 11.5. Now, the first part of Chapter 11 introduced us to the concepts of probability. And the second part of Chapter 11 is going to be about conditional probability, binomial probability, and expected value. We're going to be illustrating these with a lot of examples and problems from the text, so you want to be sure to have your text handy. Now in section 11.3, we talk about conditional probability. What happens here in conditional probability is that one event is contingent on another event. So this is written like this. If there's a probability of some event B occurring, computed on the assumption that event A has already happened, it's called the conditional probability of B given A and is denoted with this formula, P for probability of B with a vertical line and then A. So that's pronounced the probability of B given A. So the conditional probability formula is given on page 597 of the text, and this is the probability of B given A is the same as the probability of A intersecting B divided by the probability of A. And that's the probability of A and B divided by the probability of A. So if you turn to example 2 in the book, given a family with 2 children, find the probabilities that both are girls, given that at least one is a girl, and both are girls, given that the older child is a girl. So the example in the book gives us the solution. The solution is given with the sample set, S, being defined as girl, 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 boy, boy, girl, boy, boy. Now, the way that this is set up is that the first letter represents the firstborn child, the second letter represents the secondborn child. So that first event is the sample space. Set A is defined as both are girls. Set B is defined as at least one is a girl. At least one is a girl. And then set C is defined as the older one being a girl. Remember, the first child is listed in the pair. So the older one is a girl. Now the problem asks for find these probabilities that both are girls, given that at least one is a girl. So the probability of A, that both are girls, given B, at least one is a girl, is defined as the probability of A and B divided by the probability of B. Now, this is written out in the text, but I'm just going to repeat it here. The probability of A and B occurring, probability of A and B is given as A, as far as the sample space is concerned, has a probability of 1 over 4. The probability of B is 3 over 4 because there are 3 of these over the 4 in the sample space. The probability of A and B occurring regards us or causes us to look at the overlap. So the overlap is 1, both of them are girls, over the sample space of 4. 1/4 divided by 3/4 is the same as 1/4 times 4/3, and that equals 1/3. So the probability that both are girls, given at least one is a girl, is 1 over 3. And then part B says, what's the probability that both are girls, given the older child is a girl? So the probability of A given C is the probability of A and C divided by probability of C. So A and C, again, there's one intersect here, GG, so 1 over the 4 divided by the probability of C, which is 2 over 4, comes down to 1 over 2. So the probability that both are girls, given that the older child is a girl, is 1 over 2. So occasionally you'll have independent events, and 2 events, A and B, are called independent if knowledge about the occurrence of one of them has no effect on the probability of the other one. That is, the probability of B given A is the probability of B, or equivalently, the probability of A given B is the probability of A. So if you look at example 3, on page 598, a single card is to be drawn from a standard 52-card deck. The sample space S has 52 elements. Given the events, A, the selected card is a face card, and B, the selected card is black, the probability of B occurring is that there are 26 black cards out of 52. So 26 over 52 is 1 over 2. That's based on the theoretical probability formula. And then find probability of B given A. So the probability of B given A uses the conditional probability formula to determine that of 52 cards, 12 are face cards, and 6 are black face cards. So 6 times 52, 6 over 52 times 52 over 12 gives us 1 over 2. Because the probabilities are the same, these 2 events are considered independent. So in the exercise section of section 11.3, page 603, the first 2 problems for each experiment determine whether the 2 given events are independent. 1, tossing coins. A fair coin is tossed twice. The events are head on the first and head on the second. Are these independent or dependent? Give you a moment to think about that. But if we consider that the probability of tossing a head on the first one is 1 over 2, and the probability of rolling a head on the second is also 1 over 2, the second one does not depend on the first one. The probabilities are the same, so they're independent. Number 2, if you roll a pair of dice, the events are even on the first and odd on the second. Once again, the probability of the second one occurring is not dependent on the first one because they are independent. Well, they are independent events, so these are independent. The probability of rolling an even on the first is the same as the probability of rolling an odd on the second. In the last section, we talked about the addition rule of probability, but now in this section, we talk about the multiplication rule of probability. So if you have any two events, A and B, the probability of A and B is the same as the probability of A times the probability of B given A. And if A and B are independent, then the probability of A and B is equal to the probability of A times the probability of B. Let's look at the fact that these can be rearranged algebraically, and we can determine some calculations based on this. So how do we apply this? In section 11.3, let's consider the probability of drawing a heart and a queen. Probability of drawing a heart and a queen. So if we consider the word "and" here, probability of drawing a heart and a queen is the probability of drawing a heart times the probability of drawing a queen given a heart. So if you think about this in terms of our deck of cards example, there are 13 out of 52 hearts. So the probability of drawing a heart is 13 out of 52. But if you've already drawn a heart, the probability of drawing a queen from that heart selection is 1 out of 13. So the probabilities must be multiplied together. Similarly, what is the probability of drawing a diamond and a red card? Well, diamonds are red cards, so the probability of drawing a diamond and a red card is the same as the probability of drawing a diamond times the probability of having a red card given that you've already drawn a diamond. Well, once again, the probability of drawing a diamond is 13 out of 52. There are 13 diamonds in the deck. The probability of getting a red card if you've already drawn a diamond is 1 out of 1 because diamonds are red. So the probability here is 13 out of 52, and which turns into a probability of 1 over 4, or 0.25. So how do we tell if they're independent? Let's talk about the problems in exercises 13 to 16 and 17 to 20 on page 604. In this example, a pet store has 7 puppies. So this is the sample space. And they have 4 poodles. They have 2 terriers. And they have 1 retriever. If Rebecca and Aaron, in that order, each select 1 puppy at random with replacement, that is, they may both select the same one. So if one child selects a certain puppy and the second child can also select that same puppy because the puppies are put back, find the probability of each event in these exercises. So probability that both select a poodle, probability of selecting a poodle, remember, probability is the likelihood of an event occurring divided by the total number of events. So the probability of selecting a poodle, is 4/7. The probability that both would select a poodle, you would just multiply those probabilities together. So the probability that both would select a poodle is 16/49. Number 14, Rebecca selects a retriever and then Aaron selects a terrier. So the probability of a retriever for the first choice and then a terrier for the second choice is probability of retriever. There's only one of those, so 1/7 times probability of 2/7. There are only 2 terriers. So this probability is 2/49. 2. Problem 15, Rebecca selects a terrier and Aaron selects a retriever. So the probability of a terrier being selected as the first one and a retriever as the second one. Once again, this is 2/7 times 1/7, or 2/49. It's the same as the probability in the previous problem. In number 16, the probability that both would select a terrier is 1/7 times 1/7, or 1/49. This is assuming that they are just randomly selecting the puppies. Now, starting in number 17, we're talking about, suppose 2 puppies are selected as earlier, but this time without replacement. So Rebecca and Aaron cannot both select the same puppy. Find the probability of each event. The probability that both would select a poodle is, for Rebecca to choose first, probability is 4/7. Now she has taken 1 puppy out of the sample space and potentially 1 poodle. So what's left is 3 for Aaron to choose times 6. So the sample space is changed to 6. This is without replacement. So this is 12/42, and this can be reduced to 2/7. In number 18, Aaron selects a retriever. Probability of a retriever given that Rebecca selects a poodle. Well, if Aaron selects a retriever, given that Becca selects a poodle, if Rebecca has selected a poodle, that takes the sample space down to 6. There's only one retriever left, so that's 1 over 6. I'm sorry, that was number 19. Number 18 is Aaron selects a terrier. Probability of Aaron selecting a terrier given Rebecca selects a poodle. So again, there are 2 terriers. If she's already selected a poodle, that puts the sample space down to 6. There are 2 terriers left, and we get 1 out of 3. Number 20, the probability of Rebecca selecting a retriever, is 1 over 7. There's only 1, there's 7. Now, here's an interesting twist. What's the probability that Aaron would select a retriever given that Rebecca selects a retriever? Well, there's only one retriever, so if the first child selects a retriever, the probability of Aaron, the second child, selecting a retriever would be 0. And number 22, similarly, that both would select a retriever harkens back to number 21. The probability is 0. Because there's only one retriever, they cannot both select a retriever. So turning to section 11.4, is the discussion on the binomial probability distribution. This is when we have outcomes of probability experiment divided into 2 categories, success and failure. The associated probabilities are called binomial. The prefix bi means 2, as in a biplane, which has 2 wings, or biannual, which means every 2 years. The binomial probability formula is given here and is also on page 609. Now, don't be too alarmed about the binomial probability formula, because what we have here is the probability of some event X occurring. We'll take into consideration the combination formula from chapter 10. So we have a certain number, so n choose X, times the probability of X occurring, probability of the success, P, to the X power, times the probability of the failure, Q, to the n minus X power. This is expanded out like this. Let's look at some examples. Page 611, number 20. binomial probability applied to rolling dice. Now, in a rolling dice experiment, a fair die is rolled 3 times. Fair die rolled 3 times. So what this is telling us is that n equals 3. A 4, rolling a 4, is a success. So the probability of rolling a 4 is 1 over 6. There are 6 sides to the die, and there's only one 4. Rolling any other number is a failure. So this is called Q. So the probability of not getting a 4 is 5 over 6. Now, problem number 20 says, find the probability of each number of successes. So 0 successes means that x equals 0. We apply the probability, the binomial probability formula. So probability of getting 0 successes in 3 rolls of the die are 3, choose 0, times the probability of a success, 1 over 6, to the x power, 0, times the probability of a failure, 5 over 6, to the n minus x power, so 3 minus 0, or just 3. So 3 choose 0 is 3 factorial divided by 0 factorial divided by 3 minus 0 factorial times 1 over 6 to the 0 power times 5 over 6 to the 3rd power. 0 factorial, the definition of that is 1. So what we have here is 3 factorial divided by 3 factorial. Any number divided by itself is 1. So we have 1 times 1/6 to the 0 power. Any number to the 0 power is also 1 times 5/6 to the 3rd power, which is 125 over 216. So the probability of getting 0 successes is 125 2/16. Now you can convert this to a decimal just by dividing 125 by 216, and you get 0.578. So it's about a 57.8% probability that we will have 0 successes. So 0 4s will be rolled. So number 21, what's the probability of getting 1 success? Remember what a success is, rolling a 4. So the x is 1 in this case. Now we're looking at the probability of 1 success. So now we have 3 choose 1, 1 over 6 to the first power, 5 over 6 to the 3 minus 1 power. So this gives us 3 factorial divided by 1 factorial times 3 minus 1 factorial times 1 over 6 to the first power and 5 over 6 to the second power. So the probability of one success is 3 factorial divided by 2 factorial is just 3 times 1 over 6. 1/6 to the first power is 1 over 6. And 5/6 squared is 25/36. You multiply these together and you get 25/70. If you wanted to convert this to decimal, you have 0.347, or about 34.7% probability that you would have one success when you roll the die 3 times. So using the same binomial probability formula, let's jump ahead to problems 36 through 38. This has to do with the side effects of prescription drugs. It's known that a certain prescription drug produces undesirable side effects in 35% of all patients who use it. Among a random sample of 8 patients using the drug, find the probability of each event. So let's consider this problem. How many are in the sample space? We have n equals 8. They tell us that. There are 8 patients using the drug. Now, the probability of an undesirable side effect occurring is 35%, or 0.35. Now, even though this is an undesirable side effect, even though this seems like a negative thing, in terms of this problem, this is the probability of a success occurring. Okay, you have to be careful with these types of problems because the binomial probability formula talks about successes and failures. A success is not necessarily a good thing. So here we have unwanted side effects. That is not a good thing. So if the probability of success is 0.35, the probability of failure is 1 minus 0.35, or 0.65. So this is the probability of failure. So the problem states, number 36 states, that none have undesirable side effects. So in this case, X is 0. That there are 0 undesirable side effects. Okay. So the probability of there being 0 undesirable side effects in 8, in a sample space of 8, is 8 choose 0 times the probability of success, which is 0.35, to the 0 power, the x power, times the probability of failure, 0.65, to the n minus x power, or 8th power. So 8 choose 0 is 8 factorial divided by 0 factorial, 8 minus 0 factorial, times 0.35 to the 0 power, which is 1, and 0.65 to the 8th power is 0.031, 0.0318. So 8 factorial divided by 8 factorial is 1. So the probability here is 0.0318, or about 3.2% probability. In number 38, x equals 2. In a sample space of 8 with 35% undesirable side effects occurring, what's the probability that 2 would have undesirable side effects? So we set this up the same way. 8 choose 2 now. The probability of a success, that is undesirable side effects occurring, is 0.35 to the 2, and failure is 0.65 to the 8 minus 2 power, which is the 6th power. So 8 choose 2, 8 factorial, divided by 2 factorial times 8 minus 2, all of that factorial, times 0.35 squared, times 0.65 to the 6th power. So 8 factorial is 8 times 7 times 6 factorial, all divided by 2 factorial times 6 factorial. The 6 factorials cancel out. 0.35 squared is 0.1225. Add 0.65 to the 6th power is 0.0754, and we get a probability of 0.258, which is about 25.8% probability. So in the binomial probability formula, what you need to do is read the problem carefully and decide what the successes are, what the problems are asking you for, and then determine the probability of the failure, and find out what it is that the problem is actually asking you. Then plug those values into the binomial probability formula and calculate your solution. In section 11.5, we're talking about expected values. In expected value, if you have a random variable x, and it has any of the values, x sub 1, x sub 2, x sub 3, etc., and the corresponding probabilities of these values occurring are probability of x sub 1, probability of x sub 2, and so forth, then the expected value is given by the product of x sub 1 times the probability of x sub 1 plus the product of x sub 2 times the probability of x sub 2, and so on. So if you look at example 1, the expected number of boys for a 3-child family, that is the expected value of the number of boys, assuming girls and boys are equally likely. So the problem gives the sample space for the experiment. There are 3 children, so there's 3 girls. Girl, girl, boy. Girl, boy, girl. Boy, girl, girl. Girl, boy, boy. Boy, girl, boy. Boy, boy, girl. And boy, boy, boy. There are 8 in the sample space. Table 11 in the book shows the probability distribution. I'll reproduce it here. So the number of boys is 0, 1, 2, or 3 in a 3-child family. The probability, so the number of boys is the x. The probability of the x occurring, probability of 0 boys occurring is, there's only 1 set here, so 0 out of 8. The probability of 1 boy, so here's 1, here's 2, 1, 2, 3. There are 3 out of 8. Probability of 3/8. Probability of 2 boys, 1, 2, 3. Another 3/8. And then the probability of all 3 boys, again, is 1/8. So the product of x times px is 0. 1 times 3/8 is 3/8. 2 times 3/8 is 6/8, or 3/4. The probability of 3 times 8. So the expected value is that you add these up. So 3/8 plus 6/8 plus 3/8 equals 12/8, or 3/2. So the expected number of boys here is 1.5 boys. The result seems reasonable, the book says. Since boys are equally likely, half of the children are expected to actually be boys. In a family with 3 children, that would be 1.5 children. Now, obviously, this couldn't ever really occur because you couldn't have half a child, but um, the book says if we record the number of boys in many different three-child families, then by the law of large numbers, as the number of observed families increases, the observed average number of boys should approach the expected value. Some additional examples to illustrate this are in the end of this chapter. And we'll work on some of these. So turn in the end of this section to page 619, number 7. Page 619, number 7. For exercises 7 and 8, consider a game consisting of rolling a single fair die with payoffs as follows. If an even number of spots turns up, you receive as many dollars as there are spots up. But if an odd number of spots turns up, you must pay as many dollars as there are spots up. So what are the expected net winnings of the game? So let's list the information in a table. So let's say the number rolled, there are 6 numbers. So we roll 1, 2, 3, 4, 5, or 6. Okay. Now the payoff, we have to reread the problem for. What's the payoff going to be? If an even number of spots turns up, you receive as many dollars as there are spots up. So if we get an even number, we get that number of dollars. So there are 1, 2, 3 even numbers. So we would add that number of dollars to our pocket. But if an odd number of spots turn up, you must pay as many dollars as there are spots up. So you would be out $1 here, you'd be out $3 here, you'd be out $5 here. So this would be the payoff. So what's the probability that this would occur? The probability that you would roll any of these numbers is 1 over 6. It's the same probability for each one. We talked about rolling of a single die and the probability thereof before. So the product of payoff times the probability is going to be negative 1/6 of a dollar, positive 2/6 of a dollar, negative 3/6 of a dollar, positive 4/6 of a dollar. We're just multiplying these through. Negative 5/6 of a dollar, and positive 6/6 of a dollar. So the expected value is the sum of these. So negative 1/6 plus 2/6 minus 3/6 plus 4/6 minus 5/6 plus 6/6 gives us 0.50 dollars or 50 cents. So the expected net winnings for this game are 50 cents. Now, number 8 says, is this game fair or unfair against the player or unfair in favor of the player? This game is actually unfair in favor of the player since the expected value is greater than $0 for the player. Think about that. This game is unfair, but it's in favor of the player since the expected value is greater than 0. If the expected value were 0, then it would be a totally fair game. Look at number 11. This is page 620, number 11. Expected number of absences in a math class. In a certain mathematics class, the probabilities have been empirically determined for various numbers of absentees on any given day. These values are shown in the table below. Find the expected number of absentees on a given day. Give the answer to 2 decimal places. So we have the number absent. So we have 0, 1, 2, 3, and 4. The probability is 0.18, 0.26, 0.29, 0.23, and 0.04. So the expected number of absences on a given day would be to take these, the number absent times the probability, and we get 0 times 0.18 is 0. 1 times 0.26 is 0.26. 2 times 0.29 is 0.58. 3 times 0.23 is 0.69. 4 times 0.04 is 0.16. So we add these together. And we get 1.69. Now, this is the expected number of absentees on any given day. Obviously, we couldn't have 0.69 of a person, but this is the expected number. These examples are fairly straightforward, but let's look at the problems in number 29. Evaluating an insurance purchase. David Glenn, the promoter of an outdoor concert, expects a gate profit of $100,000 unless it rains. So let's write that down. $100,000 unless it rains. which would reduce the gate profit to $30,000. So this is gate profit. If it does rain, then the gate profit is $30,000. The probability of rain is 0.25. I'm sorry, 0.20. 0.20 is the probability. For a premium, that is an insurance premium of $25,000, David can purchase insurance coverage that would pay him $100,000 in the event of rain. So let's look at it this way. Event, rain, no rain. So what is David's net profit? We'll call that X in the event of rain. Well, let's assume that he buys the premium. So he would get $100,000, okay, if it rains. He would also get $30,000 in the event of rain, but he's out a premium of $25,000. Which is a net profit of $105,000. I'll abbreviate 1,000 as K. So $105,000. Now the probability is 0.2. Probability of rain is 0.20. .20 times 105,000 is $21,000. Now, in the event of no rain, he would get $100,000. I'll abbreviate that as 100K. But he's also going to be paying the premium of 25K. So his net profit is only going to be 75K. The probability of no rain is 0.8, which is 1 minus the probability of rain. Multiply 75,000 times 0.8, and you get 60,000. Add these together, and your expected profit is $81,000. Now, this is the expected profit when the insurance is purchased. Let's look at the expected profit when the insurance is not purchased. So, not purchased. Again, the event is rain, the event is no rain. His net profit is going to be $30,000 because if it rains, that's what he'll get. No rain, he'll get $100,000. he has not paid any premiums because the insurance premium is not purchased. The probabilities are the same. Probability of rain is 0.20. Probability of no rain is 0.80. Multiply these together. 6,000, 30,000 times 0.2, and 80,000, which is 100 times 0.8. This gives us 86,000 expected profit. Number 31 says, based on the expected values, which is David's wiser choice in this situation? Well, his expected profit is going to be greater if he does not purchase the premium. 86,000 is greater than 81,000, and you should not purchase the insurance. So try some of the other problems in sections 11.3, 11.4, 11.5 on the syllabus or otherwise. The full answer key for the book problems is posted on Blackboard. So email me if you have any questions. Thanks very much for your time and attention.